This time I'm going to do the key for the exam as a video because I think it makes a little more sense to actually talk through these keys rather than just have a sort of a blank explanation. So here goes. I hope it's helpful. First of all, we've got question Jerry. We're dealing in the Grateful Dead here, of course. So Jerry's worth 25 points. Jerry won 6 points. The question is, what observables are associated directly with each of these quantum numbers? And it's referring to describe the appearance of the h-wave function given by the quantum numbers in the bracket notation 4, 2, negative 2 plus a half. So what observables are directly associated with these quantum numbers, and what are the specific values of those observables for this state? And that's important. Please read these things exactly. So first of all, the observables, our quantum numbers are 4, 2, negative 2, plus a half. Okay, so 4 is the principal quantum number n. That's associated with energy, and the value is negative 1/16 of a Rydberg because it's minus 1 over n squared times the Rydberg. The next one, 2, that's L, and that's the orbital angular momentum quantum number associated with the orbital angular momentum, and the value is square root of 6 h bar because it's the square root of L times L plus 1 times h bar. The minus 2 is the z component of the orbital angular momentum. It's also called the magnetic quantum number, and that's equal to minus 2 h bar is the value of the observable. And finally we've got a plus 1/2, and that's the z component of the spin, or the spin orientation. And so m sub s, the spin angular momentum, is plus 1/2 h bar here, also known as spin up. But you've got to put in the actual values, minus a 16th Rydberg, root 6 h bar, minus 2 h bar, and plus a half h bar for full credit on this question. Also, it's really important to realize that the spin angular momentum is similar in magnitude to the orbital angular momentum, so they come in units of h bar, and they can be close to each other. Alright, so the next one, part 2, 4 points. How many radial and angular nodes are there in the electronic wave function, and how do you know? Well, you know the total number of nodes is equal to n minus 1, and that means there's got to be a total of 3 nodes, and now the angular nodes are just given by L. So the angular nodes have to be L equals 2, and that means that there's 1 node left for a radial node because it's going to be the difference. 3 minus 2 is equal to 1. Okay, now part 3 for 4 points. How are the angular nodes split between the theta and phi coordinates? Well, the cycles in phi or phi are given by the absolute value of m sub z, the phi component, the z component of the angular momentum, and that's 2. So there's 2 cycles in phi, and that's equal to the nodes. So there's 2 angular phi nodes, and that means there's nothing left because the theta nodes are the residual. That's 2 minus 2 is 0. So there are 2 nodes or cycles in phi and 0 nodes in theta. The next question is, where in space is the electron most likely to be found? What general area, not the exact spot? And I ask you to include a sketch of the radial wave function and the radial probability distribution. And finally, why are they different? Didn't leave enough space here, but you can find some somewhere. Sorry about that. So it's n equals 4, so the most probable radius is going to be big, because the radial wave function always scales with e to the minus r over n times a naught. So r over 4 Bohr radii, and there's a polynomial that's getting big as well. So first of all, the most probable radius is going to be quite large for n equals 4. Now, the radial wave function is going to have 1 node, and it's going to basically, it has to be 0 at r equals 0 because of the orbital angular momentum. It's going to go up some, it's going to cross 0, it's going to go down some, it's going to come back. The probability is proportional to r squared, the radius squared, times the radial wave function squared. There should be a squared there in that key. It's r squared, little r squared, times big R squared there. And so that is going to have a much larger value on the right-hand side, on the far distance away from the node than the secondary maximum in the inside. So the maximum farther out is much, much larger in probability even though it may be smaller in amplitude on the left-hand wave function. And there's a difference because there's just so much more space out there, because the number of points in space at a given distance from the center, from the origin, goes like r squared. And so that's why you get just a much more distribution over a large radius compared to the radial wave function. Now you could add into this as well that it's likely to be at the equator because you have all of the orbital angular momentum associated with phi, which means that there's no probability whatsoever of finding the object near the theta equals 0 or pi at the poles. It's going to be equatorial, but I didn't demand that of this exercise. Also, the actual value of the maximum r is way more than 4 Bohr radii. Actually, it kind of goes up like the square of it. It's way out there at roughly 16 Bohr radii, because the polynomial part of the wave function is actually contributing quite a lot to the magnitude until you get several e-folds down. But that's a detail that I also did not expect you to come up with. Just this basic form here. Okay. Part 5, worth 5 points. What's the electronic wave function called as an orbital, and how many total wave functions have the same energy? How do you know? Again, you got to be careful about this one. Think it through. First of all, n is equal to 4, L is equal to 2, so this is a 4D orbital. That's what we call it, a 4D orbital. That part is clear. You need both the 4 and the D to get full credit for that part of the question. Now the next one's a little bit more difficult, because in general the total energy is associated only with n, and there are spin and orbital angular momentum to account for here. So really I've got 5 by 2 is 10 functions for the 4D, but then I've got L equals to 2 and L equals 1 and L equals 0, the 4P and the 4S, and I've also got a 4F. Don't forget the 4F. In other words, we've got L equals 0, 1, 2, and 3 allowed for the n equals 4 case. I've got 10 total wave functions for the 4D, because there's 5 orbital angular momentum functions times the 2 up or down spins, so you get a 10 out of that from the 4D. You get 2L times 1 times 2S plus 1 for each of these. There's 6 total in the 4P, 2 total in the 4S, and 14 total in the 4F. So there's actually 32 total states here, and so the total degeneracy is 32. It certainly isn't 5, which you got a lot of answers. Quite some number of people answered 10, and I was reasonably kind about 10. There certainly are 10 total 4D type states, but there's also all these other states to account for. Now there's actually an alternate answer here that nobody provided. It's technically more correct. It's not really what I was looking for, but it's technically correct. So we can erase all this part. It's still a 4D, but we can go and we can say, well, what's the term symbol for this? The 4D is going to be a doublet D 3/2 for the lowest energy term symbol. I'm just picking the lowest energy because I asked the total number of wave functions with the exact same energy. And so that would be the 4D 3/2 because this is less than 1/2 full. We've only got a single electron. So J is equal to 3/2. 3/2 times 2 is 3 plus 1 is 4. So there are actually 4 states with really the same energy in this doublet D 3/2 term symbol. And you can go and look it up on the atomic database online. You'll discover that for hydrogen, you've got the 4P, 4S, 4D, and 4F. That's a doublet P, doublet S, doublet D, and doublet F states. They all have just about 102,823.904 wave numbers, but actually the let's see, the doublet P 1/2 is the very lowest in energy. It comes in at 102,823.848525 wave numbers, and the doublet F 7/2 states. So there's 8 of those guys coming at 102,823.917091. So there's a little bit of a range of energies there, but the 32 states total were essentially what I was really looking for, but I would have been quite happy to accept the doublet D3 halves and 4 states as a well-defended answer as well.